In this lesson, we'll see an introduction into dynamics portion of the syllabus and essentially set the stage for subsequent lessons. We know that dynamics can be thought of as having two branches. One is kinematics, wherein we study only about movement of objects without bothering about the causes, that is, what are the forces. And the second topic is about kinetics, which studies forces also. In the topic on kinematics, the following are essentially the topics that we are going to go through. Considering it as a particle, rectilinear and curvilinear motion. Rectilinear means along a straight line, curvilinear means along any general curve. We'll study two topics, projectile motion and normal and tangential components. These are the topics that we see through in kinematics. In the portion on kinetics, that is study of forces and its effects, we'll study essentially about Newton's second law, then work energy principle, then impulse momentum principle. All these three are in fact one and the same. They are algebraic manipulations of the same equation. Then we'll study an elementary analysis of central force motion, then fixed axis rotation and rolling bodies. Though statics was very well developed, advancements in dynamics did not begin until accurate measurement of time was possible during the time of Galileo Galilei, that is 1564 and 1642. Galileo studied pendulum as well as bodies sliding over inclined plane very much, and he made a lot of contributions to the field of dynamics. And as though he is handing over his work to Newton, he initiated the work for fundamental laws of motion. Newton formalized all that work during his lifetime of 1642 to 1727, and this was a leap of development for dynamics. The three laws of Newton and the law of gravitation more or less set the foundation for dynamics and engineering mechanics. And the Apollo space mission is a testament to the truth and usefulness of the fundamental laws of motion proposed by Isaac Newton. Once Isaac Newton proposed these fundamental laws of motion and also initiated calculus, several other developments were possible, and Leonard Euler, D'Alembert, Joseph Louis Lagrange, Euler-Lagrange dynamics, and D'Alembert's principle of reaction forces. These all contributed a lot to the field of dynamics. It is such a rich field now that one would be delighted to study the topics on dynamics. In this lesson, we will initiate the topics of kinematics and begin with the study of rectilinear motion of a particle. Okay. In this study, we will assume that particle has a mass but negligible shape and size. When we say negligible, we don't say it is very small. What we mean is the size of the object is of no consequence, because we will study the movement of its mass center and say that whatever applies to this mass center applies to all the other points. That is the reason why the shape and size are of no consequence. The object may be very big. For example, while studying planetary motions, one may consider Earth or Moon or Jupiter to be a particle of negligible shape and size. That doesn't mean that Earth is very small. Of course, it is small as compared to the galactic dimensions, but what we essentially mean is the shape and size are of no consequence. Another thing that we need to note is when you neglect the shape and size and consider only movement of the mass center, we won't steady rotation of the body. In rectilinear kinematics, we'll assume that the body moves in a straight line, and we try to define several things. We'll try to define what we mean by position, displacement, then speed, velocity, and acceleration. Let us look at them one by one. When we say rectilinear kinematics, what we are considering is a body shown to be a red dot here, big red dot here, is moving along a straight line. The straight line is what we call S-axis, just like X or Y-axis. The particle is moving along S-axis, and we have a specified origin in mind. This blue dot shown here is the origin, represented as O. Okay, we'll specify position with respect to this origin O along the axis S. That is, all the movements are occurring along this straight line. We say that when time t is equal to 0, S is equal to S0, that is this length from here to here, this directed line S0 is what we mean by position. So at t is equal to 0, S0 is the position, and this we often refer to as initial condition. At time t is equal to 0, distance is S0, velocity is V0. This we refer to as initial condition. And when we specify this S0, if this particle shown by red dot is to the right of the origin, we specify that S0 is positive. If it is to the left of the origin, we say it is negative. Because we are talking of to the left and to the right, that is, we are talking of a direction, this position is a vector quantity. Very often we refer to another quantity which we call distance. Distance is always a positive quantity, and it is measured positive scalar quantity, and this distance is always greater than or equal to 0. Having seen what we mean by position, we note that displacement is change in the position. For example, at time t is equal to t1, the particle is at the point shown by this red dot here. At time t is equal to t2, the particle, let us say, moved to a new position. Okay, at time t is equal to t1, your displacement was position was s1. At time t is equal to t2, your position was s2. So the position changed, and we say that this change is what we call delta s, that is the displacement. Okay, so delta s is s2 minus s1. We call it a vector quantity. If the final position, that is, this is the final position, assuming that t1 is less than t2, this is the initial position, this is the final position. T is equal to t1 is the initial position, t is equal to t2 is the final position. Okay, if the final position is to the right of the initial position, we say that the displacement is positive. If the final position is to the left of the initial position, we say that delta s is negative. As you might have noticed, we are gradually building on one definition over to the next definition. We started with position, and we said change in the position is displacement, and the next topic is velocity. We define what we mean by average velocity. We define what we mean by instantaneous velocity. Then we specify what is speed, and then average speed. We'll give two examples to illustrate these. Let us say you have a particle shown by this red dot here. At time t is equal to t1, at time t is equal to t2, it moved to a new position. That is, the time elapsed is t2 minus t1, which is delta t, and the displacement is delta s. The ratio of this delta s to delta t is what we call average velocity during the time interval from t1 to t2. Okay, and we see that delta t is always positive. We cannot go back in time. So delta t is always positive. So sine of delta s defines the sine of this average velocity. So if the final position of the particle is to the right, making this delta s positive, we say that the average velocity is positive. Otherwise, if delta s is negative, we say average velocity is negative. Another quantity of importance is instantaneous velocity. What we mean when we say instantaneous velocity is we take smaller and very small values of delta t and find out what is the ratio of this delta s over delta t. When you take smaller and smaller values of delta t, this ratio tends to a quantity, and that quantity is what we call derivative of the displacement, and we denote it by v. Because this ds is a vector quantity, v is also a vector quantity, this delta s is also a vector quantity, very strictly we need to put an arrow on the head, arrow on the head of this v to indicate it's a vector quantity, an arrow on the head of this delta s to indicate it's a vector quantity. Similarly, an arrow on the head of this s to indicate it's a vector quantity. But when we understand that v is a vector quantity, we kind of omit that and understand that it is a vector quantity. So this instantaneous velocity is a vector quantity. Again, we note that since delta t is always positive, we can only go forward in time. The direct sense and sine of v is the same as the sine of delta s. And when we take magnitude of this, whether v is minus 2 meters per second or whether v is 2 meters per second, the 2 meters per second is what we call speed. That is the magnitude of the velocity. You take absolute quantity and it is always positive. Another quantity that we often try to specify is average speed. Average speed over a long period of time is defined as the total distance traveled divided by the total time elapsed. These quantities could be totally different. That is average velocity and then instantaneous velocity, speed and average speed. They could be totally different quantities. We'll try to see a couple of examples to illustrate this difference. Let us look at example 1. In the example 1, this table here shows the positions of a particle. At time t is equal to 0 seconds, it is 8 meters from the origin. This 8 is plus 8, so it is to the right. And at 1 it is 9 and so on. At 1 second it is 9 and so on. All these are distances given. What is shown here is the positions of the particle at different instances of time. At time t is equal to 0, the particle is here, 8 meters, that is the distance from here to here is 8 meters. Then when time t is 1 second, it moved to the new position over here, and at time t is equal to 2, again it came back to the position. At time t is equal to 3, it moved here. Time t is equal to 4, it came back to the origin, and at time t is equal to 5, it went to minus 7. So from here to here is position at time t is equal to 0. From here the object moved here, and from here it moved to this point, and from here it moved to this point, to this point, and this point. We are required to find what is the average velocity during the time t is equal to 1 to 2, that is in between these two, what is the average velocity, and then speed in the same instant, same duration 1 to 2, then average speed during the interval 0 to 5, that is all through this movement, what is the average speed, and then what is the instantaneous velocity. We'll quickly show how we use the definitions. Displacement during t is equal to 1 to 2 seconds. That is, originally it has s is equal to 9, then it became s is equal to 8. So final minus initial is the displacement. 8 minus 9 minus 1 is the displacement, and time is 1 second. Final time minus initial time. Note that we are always taking the difference in the same direction. 8 minus 9 divided by 2 minus 1. So average velocity is minus 1 meters per second. The average speed is magnitude of this, which is 1 meter per second. And the total distance covered, you need to very carefully note this down. The particle started here, from here to here it is 1 unit, 1 meter. Again from here to here it is 2 meters. From here to here it is 3 meters. From here to here it is 5 meters. From here to here it is 7 meters. Sum of all these distances comes out to be 17 meters. 8 to 9 1, and 9 to 8 1 2, 8 to 5 3, that is 2 plus 3 5, 5 to plus 5 10, 10 plus 7 17 meters during the total time. So average speed is 3.4 meters per second. To find the instantaneous velocity, we'll fit a curve between s and t. We obtain this equation, and where t is in where I here shown here is the unit vector along this positive s direction, and we note that the instantaneous velocity is derivative of this evaluated at t is equal to 2.5. That is 2 minus 2 into 2.5, that is minus 3 meters per second is the instantaneous velocity at time t is equal to 2.5. Because it is negative, we say that at time t is equal to 2.5, the body is moving to the left. We go to the next definition, that is acceleration. Provided the velocities are known at time instances, average acceleration is defined as delta v over delta t. Again, since delta t is always positive, sign of delta v indicates the sign of average acceleration. Just as we have defined in the previous case, instantaneous acceleration is limit of this ratio delta v over delta t as the time interval is very small. Because we know velocity is ds over dt and acceleration is dv over dt, we can write acceleration to be double derivative, that is second derivative of s. In the second example, we try to find what is the average acceleration during time t is equal to 1 to t is equal to 2 in the previous case, and also what is the instantaneous acceleration when the particle is at origin. Okay, we see that the particle is at origin, t is equal to 4. At 4 seconds the particle is at origin. So we have a curve which is fit between s and t. We differentiate that, you get velocity. Evaluate what is velocity at time instant 1. Evaluate what is velocity at time instant 2. v2 minus v1 divided by t2 minus t1, which comes out to be minus 2i, is the average acceleration during time t is equal to 1 to time t is equal to 2. We can differentiate this once again to get minus 2i meters per second is the acceleration. That is when body moves according to a polynomial equation of order 2, the acceleration is constant. We'll try to see subsequent topics in lessons to count.